Hi everybody, Scott Cart here, and I've got a quick little video for you today. Hopefully it's quick. I've been asked to go through the LM317 voltage regulator and explain how to set it up and design a quick and simple circuit. Now this was something that we used in our test number 1, and I wanted to start by showing you a couple things in the data sheet. And so you'll notice that it is an adjustable voltage regulator. It's capable of running from 1.2 volts all the way up to 37. And depending on how you set it up, it can do a myriad of different things. I've used it for several of the examples in this data sheet, right from using it as a 1.2 volt voltage regulator to a 3.3, and all the way to current regulation. So that said, let's take a look at a few critical pieces of information here. So basically, it does come in different packages. We're not going to worry about that. We're not going to worry too much today about the thermals on it or its peak voltage, but I want to draw your attention to the typical applications down here. And so the first thing that we want to take a look at is the theory of operation. And the way this works is it has a voltage reference here. And this voltage reference is going to be between 1.2 and 1.25 volts. And so that's the first thing that we're going to have to keep in mind when we're designing this, is this point here is going to be 1.25 volts. And our V out is going to be some sort of reference. Now, we have to also keep in mind that our input voltage has to be a certain amount greater than the output. So you can't get right down to, let's argue 5 volts in and 5 volts out. That's just not going to happen. All right. So here's the formula to calculate V out. And so Vref, as I say, is 1.2 to 1.25, depending on which chip you're using. In this example, it is 1.25. And then we have a voltage divider that we need to work out. And the one thing that we can do is ignore this term over here, as long as we're greater than 100 microamps. And so this is for our test. This is kind of where I wanted you to kind of zone in on and really design your circuit around this example. Right? This one's very very to the point, but we wanted to have a fixed voltage here, or sorry, a fixed resistor here. All right, so let's close this. We're going to go over to our data sheet, or our blank sheet here, and we're going to start to pull in some parts. And so the first part that we're going to want is obviously the LM317. And you'll notice that there are 5 of them here. They do different things, so different current, okay, and different packages. Okay, the package that we're going to want to use today is the T. So this is the TO220 case. So I'll select that. We're obviously going to need ourselves a couple of resistors. I'm going to grab these resistors here. We're going to need some capacitors. And so I'm going to grab the non-IEEE standard, and I'm going to grab the EEE standard. I realize I'm mixing and matching here, but it's just the way I work. I like it this way. I'm also going to need a LED. So let's grab say this orange one. Why not? And what else do we need? We need some connectors. And so single inline connectors are always good. They'll be here under connectors. Where are you? We'll have to unselect our parts with models. Okay, connectoconnectors, and SIL 100-2. So this is 2 pin and 100 thou, or 0.1 of an inch spacing. We're also going to want to get ourselves a fuse. Okay, something with a part model, and this one looks perfect. And so there we go. And so a couple ways that we can do this. What I'd recommend is to start out by just making the voltage regulator work. And so once this works, we can expand to the rest of the components. Okay, so 3 pins. We have voltage in, voltage out, and adjust. You can always mirror, so Control M if the part is the wrong way around for you. And yeah, using the data sheet, we can see that our minimum sort of setup is going to involve 2 resistors that are connected to our adjust pin. So like so, and we're going to need a ground on here. So let's grab our ground. There we go. And we can start by just putting in a voltage. Let's start just to do some widgety math here and see how it's all working out. And we'll check our output voltage. Excuse me. So the first resistor, R1, is going to determine how much current is going through our network, because we know that this voltage here is going to be 1.25 volts. Okay, we can figure out what kind of current we're going to have going through here. So let's keep our math nice and easy and say that let's put a 500 ohm resistor in here. I realize it's not really a standard value, but it's good enough for now. And so if we do a little bit of math here, we can say that let's say that we just use Ohm's law, and we say that 1.25 volts divided by 500 ohms is going to be, so 1.25 divided by 500 is going to give us 2.5 milliamps. Okay, and so that's the current that's going to be traveling through here. And so if our voltage from here to here is 1.25 volts, and we wanted to have an output voltage, in this case, we want our V out to equal 5 volts, then we know that the voltage that we have down here is going to be 5 volts minus 1.25, which is going to be 3.75 volts. Now that we know the voltage here and we know the current here, we can actually calculate the rest of this again using Ohm's law. So we have 3.75 volts divided by 2.5 milliamps. Okay, so let's grab our calculator again. And so 3.75 divided by 0.0025 means that we need a 1.5K resistor. Okay, so let's sub that in. Here we go. Grab this and set you to 1K5. And if we set our DC voltage coming in, we'll just throw in some arbitrary value for now. And we'll run it. Oh, my bad. Got the wrong thing here. Let's put in a probe so that we can measure our voltage. And you can see that we are really, really close. And so how could we improve that? Well, to improve it, we could basically increase the current through here, which would reduce the effect of the leakage current or the quiescent current that's coming through the adjust. So let's just cut this down and say that this is 250 ohms, and half of the here would be 750. So I've just divided the two of them in half. And if we run it again, you'll notice that it improves it a little bit. And so as you can see, it's just a simple voltage divider. So Kirchhoff's voltage law comes into effect here, as well as Ohm's law. That's all there is to this portion. All right. So let's take a look at the data sheet again here super quick. What else do we have? We've got a couple protection diodes. Okay, we can worry about these if we want. You don't need to put them in. The same with the stiffening capacitor. We don't really need it, but it is highly recommended that we get this 0.1 in here, and that we have some capacitor here on the back. So let's drop them in as we're going here. So we'll grab a component, we'll grab our cap, and using the plus symbol, I'll rotate this around. And we'll set this to 100 nanofarad, like so. And he wants to go to ground. And we'll grab a nice electrolytic over here. And we'll toss him in over here. And 1 microfarad might be a little bit light. For this application, it would probably do, but it's nice to have some capacity there if you do have a load that's switching on a somewhat regular basis. Okay, let's take a look at the LED next. Now, the LED that we had sourced, there was a couple things that were important with it. One of them was the current, and the other the voltage. So let's get this wired in, and then we can take a good look at what those specifications were and what you needed to do to calculate the rest of the circuit for that. So ignoring the color, it really isn't relevant. The first thing that we want to do is basically we're going to skip over all of these absolute maximum ratings. Nobody wants to run their LEDs or any device at 100%. Okay, so I'm going to go down here to the operating characteristics. And what I'm looking at is the forward voltage and the test current. So we know that at 1.9 volts, it's going to draw about 2 milliamps. So that's nice and light. Okay, so these are the numbers that I'm going to drop into my characteristics of this LED. So just double clicking on it, I'm able to come in here and change the 2.2 to 1.9 and the 10 milliamps down to 2. And because I've used this package, I can actually go in and change the LED footprint at the same time. And the LED package that I want is called LED. Okay. And that is perfect. And so now if we give this another test run, obviously the LED is not going to, okay, the LED shouldn't come on, but it does because it's set to digital. So if we set it to analog, it shouldn't come on now, and it's very, very dim. So that's perfect. So again, we're going to go in and do a little bit of Ohm's law. So let's see. We have our voltage is 5 volts minus a 1.9 volts, right? Is going to be our voltage that our resistor needs to drop. And we can divide that voltage by oops, my bad. We're going to divide that by 2 milliamps. Okay. And so let's grab our calculator one more time. And so we had 5 minus 1.9 means that we're dropping 3.1 volts divided by 0.002. Okay, so we're looking for something about 1.5 to 1.55 K. Okay, so we can change this out now to 1.6K. 1K6. Good enough. and we give it a test. It should be nice and bright now. Fantastic. That's good. That's good. So let's keep moving backwards now. The next thing that we wanted to do is we had a mandate for a fuse. So let's pop in the fuse, and we wanted to set it to 1 amp, which it already is, and that's perfect. And I'm going to call mine FU1 for fuse. Okay, it's really important that we do include a name, or it will be excluded from our PCB. I'm just going to hit P here. I'm going to pick another part. We needed a battery, so I want a multi-cell battery. Perfect, multi-cell. There's the same, so we'll pull that in. And we will connect the positive here. And we didn't want 9 volts. In this case, we're actually going to be running it off of a car battery, so 13.5 volts. And again, I'll just grab another ground. You don't need to have all separate grounds, but it is an option. All right, and so it seems to still be running. We still have our 5 volts. That's fantastic. And the last thing that we needed to do for the design was we want to actually be able to test this we wanted to test at 500 milliamps. So I'm just going to call this RL, and I'm going to exclude it from my PCB. And so 5 volts at half an amp means that we're going to be drawing or require 10 ohms. So again, 5 volts divided by 0.5, right, is 10. Okay. And here we go. Let's grab a current probe here, and we'll make sure that we have our minimum 500 milliamps when we're running this. And fantastic. So we can see that the fuse is warm, but it hasn't blown. Okay, so we've got 500 milliamps going through our L. Finally, we'll put in our 2 connectors. So here we are here. And so one thing that I will do is I will make sure that the number 2 here is going to be my ground. So I want to make sure that it's the same. So I'm going to mirror it on this side. So pin 1 is coming in, pin 2 is going out. Let's drag that down. There we go. Perfect, perfect. And so this is basically going across the battery, which will be excluded from my PCB, through the fuse, through the voltage regulator, and then out through J1. And so I could even call this in and out to make my life a little bit easier. Okay. And what else do we want to do? We definitely want to set this up so that we let's place some wire labels on our power net. So here we are. I'm going to set this to a power. Let's create a new net class, and I'm going to call this one power. Okay, and there we go. So class equals power, and we're going to want to follow that through. Okay, place a wire label again for power, and finally here for power. And so why am I choosing these for power? Basically, anywhere that I'm going to have that 500 milliamps running, so through the ground is already class power, but across here is also class power. This one is not going to see a lot of current, so we're not worried about it. And we're not going to see a lot of current here through the LED. Okay, so we're going to set those aside for a second. All right, let's pop over to our PCB layout now that we have our schematic finished. and I'm going to go into my design rule manager, and we're going to modify our classes here a little bit. So I asked for the power to be set up that our trace style was a T20. Okay, and I wanted my signal stuff set to T12. All right, and so this means that as long as our automatic trace style selection is selected, it will pick the right size. All right. So I'm not going to start by laying down the PCB. I'm actually going to go through and pick the parts first. Okay, so one trick that we can use when we're picking these parts is to basically separate this. So I'm just going to pull this over here for a second. And let me just pin this to the side. And I want to pin the circuit. So on one side I have the circuit, the other side I'm going to do the layout. And this is a really handy way to do this so that you can follow through with the flow of power. And so the first thing that I'm going to do is I'm going to grab my in and I'm going to place it. And I already have it kind of sort of in my head how I want to lay this out. I'm going to take it off metric just because everything on the circuit board is imperial. So we'll do that. And so here's pin 1 at the top even. So that's all lining up perfectly. And the next thing that I come into is the fuse. And notice my fuse isn't here. So I'm going to go back to my schematic. I'm going to double click on this fuse. And I see that it is excluded from the PCB. So let's get rid of that. And we can see it pop up over here with a little X. And so the easy way to do this is when I try to place it, it's going to ask me, do you want to pick one? And so I'll say yes. And I told you in the test that you could use the Res 50 package for this. All right. And so that's going to be great. And I'm going to toss mine here. All right. The next thing that I see here is a C1, this 0.1 microfarad capacitor. And I wasn't really specific about footprints for that. And so we'll just use this guy. We'll toss him in here. Here we go. Nicely lined up. The next thing that we run into is the LM317 itself. U1. Perfect. And there's a nice way and an ugly way to lay that out, but that's okay. We'll put it in here like so. Then we have our voltage divider, R1 and R2. So let's grab R1. Sure, why not? Right there. And R2. Look at how nicely that all wants to line up. It's just begging for symmetry, isn't it? All right, so the next thing after that is C2, our nice big 10 microfarad capacitor. C2. Then we have our diode and resistor. So D1, there we go. And our resistor. What else do I see here? My output here. I'll toss you down here somewhere. And I'm wondering why RL is still here. I thought I excluded it. I did not. Okay. And that gets rid of that. So that's reasonable. I can live with this. I'm not too awfully fussed about any of it. So let's get a board edge around this next. And so when we select our 2D mode here, come on you. We want to make sure that we are in board edge. Come on, give me a hard time. There we go, board edge. And you obviously want to make sure that there's enough room around this to run any traces and all of your components sitting nicely on it. I even like my silk screen to be on it. I could move that, give us a little bit more room, but that's good enough. The other thing that we want to do is, so I'm not happy with this. I really like my pads sticking out the other side. There we go. So they're kind of flipped and flopped, but they're still R1, R2. And you know what? Maybe this is a great opportunity to show you how you can switch this around. So, so the labels R1 or 1 and 2 are a little bit ambiguous. I mean, nobody really cares what the numbers are, but if you wanted the top to match the top, then we can simply mirror this and then correct the orientation like so. Oops. Deleted something I shouldn't. There we go. So now that makes a little bit more sense. So the next thing I want to do is I actually want to go in and create that power plane on the bottom, and we'll attach it to ground. You'll see a lot of the connections actually just disappeared, right? And I could hit the auto trace, but this is so darn simple at this point, it's hardly worthwhile. And so let's see if we can do this all on bottom copper, because, you know, why not? And the beauty here is that because we took the time to lay it out in a logical fashion, it really isn't that difficult to get this all strung around, because it wants to run logically, because that's the way we laid it out. All right, so this one's going to be a little tight. Can we make it through here? Oh, look at that, eh? Typically, I don't like running through my pads like this, because if something ever happens to the pad, you've got a bit of an issue. But there we go. That's the board laid out now in just bottom copper. So we've ended up with a single-sided board. This is possibly one of the cheapest power supplies that you could ever make to charge your phone. And if you were doing something like running a Raspberry Pi and you needed 3.1 or 5.1 or 5.2 volts, the LM317 is great because you can adjust it to exactly what you need. All right. Hopefully this was helpful. You can see how easy it is to set up the LM317. If you like this video, give it a thumbs up. Love to hear your feedback. And for those that aren't students, if you've been shying away from a adjustable voltage regulator, there's no need. They're nice and simple. All the information's in the data sheet. And don't be afraid. Jump in with both feet. All right. Thanks, and have yourself a great day. Bye now.